problem, we counted the revolutions per minute and got 33. Average radius of a rotor ride is 5 meters.
To the amusement park, there's a ride called a rotor ride, which is essentially a cylinder that spins in a circle, and once it reaches its maximum speed, the floor drops out and you stay against the wall and don't fall down. This is due to a force of friction, in this case static friction, because you're not moving up and down, you're staying in the one place.
Okay, so first we have to go through the dynamics protocol. Is this a dynamics problem? Yes, it is, because a lot of forces are at work here, especially the force of friction. The next step is we say, oh shit. Step 2 is that the sum of the forces is equal to mass times acceleration. Step 3, we draw our free body diagram. So we have the force of gravity acting downwards. We have the force of static friction acting upwards, because when the bottom falls out, the person stays up against the wall, so we need a force acting up, keeping him from falling down. And then we have the normal force acting this way, because he's up against the wall right here. Step 4, is the system in equilibrium? No, it's not. So again, we can say that the forces is equal to mass times acceleration. And step 5, we solve.
Now we're going to sum our forces in the y direction. So it's force of friction minus force of gravity, because the forces are in opposite directions, and because the person's not moving up or down, the sum of forces in the y direction is equal to 0. So then the force of friction equals the force of gravity. Force of friction equals mu times normal force, and force of gravity is mass times gravity. So mu equals mass times gravity divided by normal force. Now we're going to sum our forces in the x direction, and the only force acting on it is the normal force. So mass times centripetal acceleration, because it's moving in a circle, equals normal force, and this is the equation. So now, since we're solving for mu, and we didn't know the normal force, and we found it here, we substitute it in and get this equation, and the masses cross out. We have our gravity, our omega squared, and our radius. So the second squared crosses out, the meters cross out, and we're left with 0.17 as our coefficient of friction.
The coefficient of friction of the wall must be at least 0.17, because you cannot control what type of clothing material the riders wear. And this ensures that when the ride gets going fast enough and the floor drops out, the person doesn't fall with the floor.
To see how a rotor ride works in action, we headed over to the Cal Poly Rec Center. We recruited some eager volunteers and placed them inside a swimsuit dryer. Then, after spinning our volunteers in the rotor ride for a few seconds, we lifted the top to see what was happening inside. A common misconception is that when you are riding a rotor ride, you think that there's a force pushing you against the wall. This is false. There is no such thing as a centripetal force. As we showed in the free body diagram, there is only the normal force of the wall, force of gravity, and force of friction in the y direction. The reason why you feel like you are being pushed back is that your body wants to continue in a line tangent to the curve, yet the walls of the rotor ride keep you going in a circular motion.